This is SpaceTime, Series 20, Episode 36, for broadcast on the 10th of May, 2017. Coming up on SpaceTime, the closest ever stellar orbit seen around a black hole. A new study of gamma-ray flashes emanating from earthly tropical storms. And scientists create what they claim is negative mass. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered what appears to be the tightest ever stellar orbit around a black hole. The findings, reported in the monthly notices of the Royal Astronomical Society, could help astronomers better understand the strange gravitational dynamics surrounding stellar mass black holes. The unusually close-in orbit, which takes just 28 minutes to complete, was discovered in a binary system known as X9, located some 14,800 light-years away in the 47 Tucang globular cluster. Globular clusters are tightly packed balls containing hundreds of thousands of stars. These stars were all originally formed at the same time from the collapse of the same molecular gas and dust cloud. They usually orbit around the galactic halo and are among the oldest known structures in the universe, with some having been dated to more than 10 billion years of age. It's thought there are more than 150 globular clusters orbiting the Milky Way galaxy. One of the study's authors, Associate Professor James Miller-Jones from Curtin University and the International Centre of Radio Astronomy Research, says it could be the tightest orbital dance ever seen by a black hole and a companion star in our galaxy. The discovery was made using the CSIRO's Australia Telescope Compact Array at Narrabri in outback New South Wales, and two NASA space-based telescopes, the Chandra X-ray Observatory and NuSTAR, the Nuclear Spectroscopic X-ray Telescope Array. While astronomers have known about this binary for many years, it wasn't until 2015 that researchers determined that it was most likely made up of a black hole pulling material off a companion star. New observations from Chandra showed that the system consistently changes in X-ray brightness every 28 minutes, which would be the likely length of time it takes the companion star to make a complete orbit around the black hole. The authors also detected a large amount of oxygen in the system. That makes a strong case that X9 contains a white dwarf star orbiting a black hole at just 2.5 times the average distance between the Earth and the Moon. White dwarfs are the stellar corpses of sun-like stars. Having exhausted their nuclear fuel supplies, their outer gaseous envelope separates from the stellar core and gently floats off into space as a planetary nebula. All that remains then is the white-hot stellar core, a super-dense ball of carbon and oxygen about the size of the Earth, left to slowly cool over the eons. It's a fate our own sun will face in about 7 billion years' time when it too becomes a white dwarf. The authors found that the white dwarf in X9 is so close to the black hole that material being pulled away from the star is forming an accretion disk around the black hole. There, matter is stretched, crushed and ground at the subatomic level before passing the event horizon and then falling forever into the black hole singularity. Astronomers think that despite the closeness of this orbit, the white dwarf's moving fast enough that it will remain in orbit and won't fall into the black hole. However, while the white dwarf doesn't appear to be in danger of either falling in or being torn apart by the black hole, its ultimate fate is uncertain. The white dwarf may have been losing gas to the black hole for tens of millions of years. If so, it's probably already lost the majority of its mass by now. And if that's the case, then over time, the star's orbit should get wider and wider as even more mass is lost, eventually turning the white dwarf into a sort of exotic giant diamond. Astronomers aren't sure how the black hole got its close binary partner. One possibility is that the black hole smashed into the white dwarf while it was still a red giant. And as gas from the outer regions of the star were ejected, a binary was formed containing the black hole and the white dwarf. The orbit of the binary would then have begun shrinking as gravitational waves were emitted. That is, at least until the black hole started pulling material off the white dwarf. Mind you, it's hard to tell because the gravitational waves being produced by the binary would have had a frequency too low to be detected by ground-based facilities like LIGO, the Laser Interferometer Gravitational Wave Observatory. However, it's possible that future space-based gravitational wave observatories, such as the upcoming LISA mission, could be sensitive enough to detect them. An alternative theory would involve a neutron star that's being spun up as materials pulled away by the black hole, much like a spinning top as you pull the string from around the middle to make it go. The problem is this theory doesn't explain everything astronomers are seeing here. Miller-Jones says that means the best current explanation to explain what they're seeing involves a white dwarf in extremely close proximity to a black hole.
A couple of years ago, we were observing this cluster 47 TUC with the Australia Telescope Compact Array. So this is an array of 6 radio telescopes in New South Wales, and we made the deepest radio image of that cluster to date. And we noticed that this source, that was a known X-ray source and had been for a couple of decades, it was the brightest radio source in the cluster, in fact. And so that made us think, because we don't know that many different kinds of system that could produce that amount of radio emission given the X-ray brightness that we see from. The ratio of radio to X-ray emission was too high to come from an accreting white dwarf system, which is what this had been previously flagged up as. This was a known source. It had been studied. It was a relatively bright blue source that's in the optical and UV bands. That was how it had first come to people's attention 20 years ago or so. So given that it produced this very bright radio emission, there were only 2 known classes of source that could explain this, and one was that it was an accreting black hole. The other one was that it was a particular class of accreting neutron star called a transitional millisecond pulsar. And so we looked into it a bit further as to what this could be. Now, if it were an accreting black hole, its relatively high X-ray luminosity would suggest that either it had to have a relatively long orbital period, in which case we should see a relatively bright giant donor star, or a very, very short orbital period, which would suggest that it should be a compact white dwarf as a donor. So we made a prediction that if this were really a black hole, which would be the best explanation for why it had bright radio emission, the donor star should be a white dwarf. This latest publication has told us something about the donor. It has not confirmed either way as to what the accretor should be, whether it's a black hole or whether it's a neutron star. But what we do know is that we have seen a 28-minute periodicity in the X-ray data. So this cluster has been incredibly well studied in the X-rays since the early 2000s.
So this is really close in, isn't it? This is like just, a couple of Earth-Moon distances apart?
The actual orbit, yes, that's right. So the orbit is about 2.5 times the Earth-Moon distance. And so that means that you can't fit a normal star inside that kind of an orbit. The star would be too big. So it has to be a very compact kind of star, something like a white dwarf. If, this being the orbital period, basically that means that the donor star really needs to be a white dwarf. So we can certainly say that. And the other piece of evidence that we have to say that it's a white dwarf is, in this latest paper, we looked at the X-ray spectra, so how the X-ray intensity varies with energy, and we saw some very characteristic lines in the spectra that came from highly ionized oxygen. So we did some very detailed spectral modeling of the X-ray emission that we saw from the source.
We know that white dwarfs are basically the cause of sun-like stars. They've burnt up their hydrogen and helium, and sort of what they've got left now are these dense cores of oxygen and carbon.
That's right. So the sun will turn into a white dwarf one day when it runs out of nuclear fuel. Exactly as you say, it runs out of hydrogen fuel in the core, and it runs out of helium fuel in the core, puffs off the outer layers, and that gives us these beautiful planetary nebulae that we see that are favorites of backyard telescopes and amateur astronomers all over the world. And what's left behind is just a very dense core of the fusion products from burning hydrogen and burning helium. So yes, you tend to have a carbon-oxygen core. A white dwarf is about the radius of the Earth, typically, and its mass is, something in the range of, half the mass of the Sun, up to maybe 1.4 times the mass of the Sun.
I think Joan Crawford would be happy with a diamond that size.
Indeed. Well, a few years ago, a group of pulsar astronomers found an orbiting companion that was very much like what we think this donor is going to turn into, and they called it the diamond planet, of course. So this is, something that is a few percent or, fraction of a percent of the mass of the Sun, made up of pure carbon, effectively. And that, obviously would be a fantastic kind of diamond if it's in that kind of crystalline structure, which, the internal structure of these things is going to be a very interesting topic of study, I'm sure.
Looking at what's going on there, what do you think's happening?
In our preferred scenario, so looking at all the evidence that we have, as I've said, we don't have a smoking gun to say whether the accretor, the massive body onto which the mass from the white dwarf is flowing, we don't know if that's a black hole or a neutron star. We think that it's a black hole from how radio bright it is, looking at some carbon spectral lines in the ultraviolet spectrum, etc. So we think what's happening is that a few tens of millions of years ago, a white dwarf got very, very close to a black hole. Now, there are various ways in which this could have happened. It could have been captured. Remember, this is in a globular cluster, a very dense cluster of stars. And so the stellar collisions, which are incredibly rare in most of the galaxy, in these very, very dense clusters where you have 1 million stars in a volume of space just a few light years across, you can actually get collisions and, close encounters whereby the strong gravity of, say, a black hole could capture a companion that passed too close and capture it into orbit. So in some way, a black hole would have picked up a companion. That companion, the white dwarf, would have got closer and closer and closer as the two emitted gravitational waves, and eventually mass would have started being transferred from one to the other. The other more spectacular explanation for how that could have arisen would be, say, a black hole kind of collided with a red giant, and then most of the envelope of the red giant was expelled, and we were just left with the core.
Yeah, that's
Either
the
way,
one I
we
like.
think
That would be spectacular.
Much more to watch, right?
Just imagine it.
Not all of that mass is going to fall into the black hole. A lot of it will be expelled from the system and just go into the gas in the cluster itself. But absolutely, it would have been very, very spectacular to see. But that would have been millions of years ago, we think. So unfortunately, we would have missed it. Anyway, so what we think happened was that the white dwarf, remember, it's a very compact remnant. So it's got very strong gravity, and it can hold on to its mass much better than a normal, say, sun-like star. So it would have to get very close to the black hole before the black hole could start pulling mass away from it, before the gravitational force on a piece of gas to the surface was stronger towards the black hole than towards the white dwarf itself. Once mass starts being transferred to the white dwarf onto the black hole, that actually causes the orbit to get wider. So to conserve angular momentum, basically, as mass flows onto the more massive accretor, we think, the black hole, the orbit gets slightly wider and slightly wider. Obviously, as the white dwarf is losing mass, it's shrinking, it's less well able to hold onto that gas. And so it continues to transfer gas to the black hole, although the rate at which that happens gets slower and slower over time. So over time, we think that this system would have evolved from an orbit period of maybe just a few minutes to what we see now, which is 28 minutes. And so over time, we think that this system, the orbit, will continue to get wider. The white dwarf will continue to lose mass at a lower rate, and we will end up with something potentially a bit like that diamond planet I was talking about before.
What's the hope now? Is it the primary objects fully identified?
That's obviously the most important thing to figure out at this point. That would really allow us to characterize the system. As I said, we definitely think it's a black hole from putting together all the evidence that we have from all sorts of different bands across the electromagnetic spectrum. But as I say, we don't have a mass determination for that object yet. So we are looking, and we've been investigating various ways in which we could go about that. We've applied for extra telescope time on things like the Hubble telescope to start to get a bit more of a handle on what we could do with, say, optical spectroscopy. But yes, we'd really like to nail down what that is. Either way, whether it's a black hole, whether it's a neutron star, it's a very interesting object. We know a fair few neutron stars in the galaxy with a white dwarf companion and a very short orbital period. We don't know of any black holes in the galaxy with a white dwarf companion as yet. So this would be the first one if we confirm it. We do know of a few in external galaxies. There's one, so the best candidate is in a galaxy in a Virgo cluster. And that probably has an even shorter orbital period, although, again, we don't have a direct measure of what the period is. But simply from its X-ray brightness, we think that it should be losing mass faster and therefore be in a tighter orbit. But yeah, so for this one, what we would really like to do is to try to verify whether or not this is indeed a black hole as the primary object in this system. Because if so, it really would be the first one of these in the galaxy to be confirmed.
Once you have the mass, I know you're going to have all other evidence as well, spectral composition, that sort of thing. But just based on the mass, how does one determine whether it's a black hole or a neutron star? I'm assuming if it's more than 1.4 times the sun's mass, then it's probably a neutron star. And how much more massive than that would it need to be before you think, oh, this is probably a black hole?
Yeah, so typically the threshold at which we think something has to be a black hole is about 3 times the mass of the sun. So we don't have a quantum theory of gravity. We don't know the equation of state of a neutron star. So we don't know how a neutron star is built. We don't know what it's made up of because we don't know how matter behaves under such extreme densities and in such extreme gravitational fields. And that's one of the core goals of high energy physics and astrophysics, to find out, how does matter behave under these very extreme densities. And that's one of the reasons people are very interested to study neutron stars. But our best guesses and all the theoretical models, and we don't know which one is correct yet, but all suggest a maximum mass for a neutron star of somewhere in the range 2 to 3 solar masses. So we think once you get above about 3 times the mass of the sun, it pretty much has to be a black hole. We know of no force that can support an object more massive than 3 times the mass of the sun against its own gravity if it's not actively undergoing fusion. So measuring a high mass for the object would convince us that it's a black hole. If the mass is somewhere between 1.4 and say about 3 times the mass of the sun, it's more likely to be a neutron star, of course.
So anything less than 1.4, you've got electron degeneracy. Anything more than 1.4 and about 2 or 3 times the solar mass, you've got neutron degeneracy. What happens beyond neutron degeneracy? Do we know? Is there, quark degeneracy? Is there such a thing? Or what do we call that? Or is that where gravitational chromodynamics comes into the whole thing and it starts to get really confusing?
Absolutely. So we don't have a theory for anything that could prop things up once neutron degeneracy fails. So neutron degeneracy, basically neutrons don't like being squished together. They don't want to be in the same quantum state, which means that if the gravitational force gets so large that it's compressing them into too small a volume, effectively they have to be pushed up into higher energy levels, and that gives you an external pressure. But that breaks down, we think, somewhere around 2.5 to 3 times the mass of the sun. Now, depending on what the inside of a neutron star is really made up of, if it's free quarks, if it's strange matter, or whether it is just very dense neutrons, depending on that, then the equation state will be different. But to my knowledge, there are no theoretical predictions for any kind of model that know how you support something once you got above about 3 times the mass of the sun. At that point, we think it has to just collapse directly into a black hole.
So it's a singularity.
Yes. Surrounded by the event horizon, of course, which prevents us from seeing the singularity. But that's where the escape speed exceeds the speed of light, and so we can't get any information out from what goes on inside.
That's Associate Professor James Miller-Jones from Curtin University and the International Centre for Radio Astronomy Research. And this is SpaceTime. I'm Stuart Gary.
Okay, now let's take a break from our show and welcome a new sponsor, Marley Spoon. One of the guys who helps me produce SpaceTime, Hugh, put me on a Marley Spoon. Tell me all about it.
What they do is they create these really nice recipes, source all the ingredients and everything, pack them up into a nice big box and send them to you. Nice and easy. And talk about making cooking simple.
You've put me on a Marley Spoon because you're a bit concerned about my diet, which is primarily takeaway. So
I reckon, Stuart, if you tried Marley Spoon, we could change you. We could sway you over to becoming a chef. That's how good they are, I reckon. Because I'm not a chef. And I ordered it up to give it a try for the program. And the recipes that they supplied...
Are they hard to follow?
No, simple. And in no time at all, you've made something really nice. And even my children were quite complimentary about the food. And that never happens in our household, I have to tell you.
Now, I've got to tell you, I can burn water. Can I follow these instructions?
You could follow these instructions, Stuart. Anybody could follow these instructions. They are so simple. I mean, as I said, I am not a chef. And I was turning out these gourmet dishes that I could fake my way through. It was fantastic.
All right. What about if you've got special tastes? Like, for example, I'm a vegan.
Yep, they've got you covered, Stuart. No problems at all. You will find vegan options on the menu. I'm gluten-free, for instance, and I was able to find some gluten-free options on there as well.
Is it expensive?
No, it's not expensive at all. We were able to absorb it within our normal weekly grocery shop bill. We have a certain budget each week for groceries, and we were actually able to reduce our supermarket shop as a result. Now, Stuart, we've got a really special offer for our SpaceTime fans. If you're living in Australia, head over to marleyspoon.com.au, and when you sign up and use the code SPACE on the checkout, you'll get $35 off your very first order. And for our North American listeners in the USA, if you go to marleyspoon.com, you can use SPACE at the checkout as well and get $30 off your first order as well.
So Marley Spoon, changing the way you cook.
And now, back to our show. Scientists have discovered that a storm's size and intensity doesn't affect its production of terrestrial gamma ray flashes, some of the highest energy sources found on Earth. The findings, reported in the Journal of Geophysical Research Atmospheres, is based on data collected by NASA's Earth-orbiting Fermi Gamma Ray Space Telescope. About 1,000 times every day, thunderstorms fire off fleeting bursts of terrestrial gamma ray flashes. Terrestrial gamma ray flashes last less than a millisecond, but they produce gamma rays with tens of millions of times more energy than visible light. Amazingly, we didn't even know they existed until 1992. That's when they were first noticed by NASA's Compton Gamma Ray Space Observatory, which was actually hunting for gamma ray bursts, intense short-lived blasts of gamma rays produced by some of the most powerful explosions since the Big Bang itself. These gamma ray bursts, which can be generated billions of light years away, are produced by events such as merging neutron stars and supernovae forming black holes. Quite unexpectedly, Compton began picking up gamma ray flashes emanating from Earth. Ever since its launch in 2008, NASA's Fermi Gamma Ray Space Telescope has kept an eye out for terrestrial gamma ray flashes. So far, it's recorded more than 4,000 of them. The data is providing scientists with a better understanding of how this phenomenon relates to lightning activity, to storm strength, and to the overall life cycle of a storm. Now, for the first time, NASA scientists have analysed dozens of terrestrial gamma ray flashes launched by some of the largest and strongest weather systems on the planet, namely tropical cyclones, hurricanes and typhoons. The study's lead author, Oliver Roberts from NASA's Marshall Space Flight Center in Huntsville, Alabama, says the data shows that storm intensity alone isn't the key factor in producing terrestrial gamma ray flashes. Roberts and colleagues found only a few gamma ray flashes being made in the outer rain bands of major storm systems, often hundreds of kilometres from the powerful eye walls at their centres. But they also found one very weak storm system which was generating several terrestrial gamma ray flashes every day. Scientists suspect that terrestrial gamma ray flashes are generated by strong electrical fields near the tops of thunderstorms. Under the right conditions, these fields can become strong enough to drive an avalanche of electrons upwards at nearly the speed of light. And when these accelerated electrons race past air molecules, their paths get slightly deflected, and that causes the electrons to lose a bit of energy, emitting high-energy photons in the form of gamma rays. As well as searching for gamma ray bursts, Fermi can also detect terrestrial gamma ray flashes, occurring within about 800 kilometres of the location directly beneath the spacecraft. Then in 2012, Fermi scientists used new techniques which effectively upgraded the instrument, thereby increasing its sensitivity and leading to a higher rate of terrestrial gamma ray flash detections. This enhanced discovery rate also allowed the authors to determine that most terrestrial gamma ray flashes are also generating a strong pulse of very low frequency radio waves. These signals were previously only attributed to lightning. The Fermi team then collaborated with scientists from the Total Lightning Network and the Worldwide Lightning Location Network, which are capable of pinpointing both lightning and also radio pulses produced by terrestrial gamma ray flashes anywhere on Earth within 10 kilometres. By combining the data, the authors were able to connect the outbursts with individual storms and their components. The authors then studied 37 terrestrial gamma ray flashes associated with numerous tropical cyclones, hurricanes, major storms and typhoons. Roberts says the study found that Hurricane Julio generated the most terrestrial gamma ray flashes of all, firing off 4 within 100 minutes on August 3, 2014, and then one more the following day, but then, amazingly, none after that. So it would seem most of this activity occurred early on, as Julio was undergoing rapid intensification into a tropical depression, but this is all long before it had even become a named storm. The authors found terrestrial gamma ray flashes generated by major storm events like cyclones and hurricanes don't appear to be any different from those produced by normal thunderstorms. In fact, it seems that weaker storms are actually capable of producing greater numbers of terrestrial gamma ray flashes, and it seems they could arise from pretty well anywhere within the storm. But in more developed systems like hurricanes and cyclones, terrestrial gamma ray flashes are more common in the outermost rain bands, the same areas which also host the highest lightning rates in these storms. Most of a tropical storm's terrestrial gamma ray flashes appear to occur as the system's intensifying. It would seem that strengthening updrafts drive clouds higher into the atmosphere, where they can then generate powerful electrical fields, setting the stage for intense lightning and for the electron avalanches thought to produce terrestrial gamma ray flashes. This is Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Physicists have created a fluid with what they say is negative mass, and it's a claim which is every bit as mind-bending as it sounds. It means that, unlike just about everything else in the universe, if you push against this negative mass substance, instead of moving in the direction being pushed, it moves in the opposite direction. A report in the journal Physical Review Letters claims the new work will help scientists exploring some of the more challenging concepts of exotic cosmic phenomenon such as neutron stars, black holes and dark energy, places where experiments aren't possible. The research provides a new way of looking at Sir Isaac Newton's second law of motion. Force equals the mass of an object times its acceleration. F equals ma. But instead of force equaling mass times acceleration, it becomes acceleration is equal to a force divided by the object's mass. And by making the mass negative, it should have negative acceleration. On paper it works, but the big question is, would it work in the real world without breaking the laws of physics? Previous research has suggested that negative mass might just be possible without breaking Albert Einstein's general relativity theory. One of the study's authors, Assistant Professor Michael Forbes from Washington State University, says hypothetically matter can have negative mass in the same sense that an electric charge can either be positive or negative. And he admits people rarely think in these terms, and of course our everyday world only sees the positive aspects of mass. If you push an object, it will accelerate in the direction you're pushing it. In other words, mass will accelerate in the direction of the force. That's what most things do. However, with negative mass, if you're pushing something, it accelerates towards you. Forbes and colleagues created the right conditions for negative mass by cooling rubidium atoms to just above absolute zero, minus 273 degrees Celsius. This converted the rubidium atoms into a Bose-Einstein condensate, a state in which all the atoms synchronize and move in unison as if they were one single giant atom. In this state, first predicted by Albert Einstein and Sathyendranath Bose, particles move extremely slowly, following the strange predictions of quantum mechanics rather than classical physics. Now this means that the particles start behaving like waves. They also begin to act as a superfluid, flowing without losing any energy. The authors created these conditions by using lasers to slow the particles down, making them colder, and allowing hot high-energy particles to escape, sort of like steam. That cooled the material even further. The lasers also contain the atoms in a containment field, as if they were trapped in a bowl measuring less than 100 microns across. Now at this point, the rubidium superfluid still has regular mass. However, Forbes and colleagues then used a second set of lasers to kick the atoms back and forth, changing their spin. As the rubidium in the center pushes outwards, the containment field is broken, allowing the rubidium to escape, rushing out fast enough to behave as if it had negative mass. Forbes says once you push, it accelerates backwards, as if the rubidium hit an invisible wall. He says the new technique avoids some of the underlying defects encountered in previous attempts to understand negative mass. It does this by providing greater control over the experiment. In fact, Forbes says the exquisite control he and his colleagues had over the nature of this negative mass should allow the team to study this very peculiar fundamental phenomenon without any other complications. However, it's worth remembering this is still early days, and other teams are yet to replicate the results. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important, or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.